Hi guys, I'm Monica. I welcome you all to my channel Aerocar. So, in our journey of aerodynamics, today we will be talking about how to calculate a drag over a two-dimensional body. In our previous videos, we learned continuity and momentum equations based on the physical principles of conservation of mass and conservation of momentum. Now, in this video, what we are going to do is apply those two equations that we had derived on a two-dimensional body, that is flow over a two-dimensional body, and see that how we can calculate drag from those equations. So without any further delay, let's get started. So here you can see that we have considered our two-dimensional body as an aerofoil, and this technique what we are going to use to calculate the drag here, this is frequently used in aerodynamics when we study about the flow behavior. Now as you can see, we have an aerofoil as a two-dimensional body, and it is surrounded by a control volume. This is our control volume that we have considered around this aerofoil, and let us name this control volume as A, B. Then let us put this as C, D, E, F, and G, and this would be our H. And now these streamlines, the AB and HI of the control volume, as we can see, they are far away from the two-dimensional body that we have considered, that is the upper and the lower streamlines. And the lines that are perpendicular to the flow, that is AI and BH, even these are far away from the two-dimensional body that we have considered. And then there is a cut that you can see, there is CD and FG. This wraps around the surface, and this DEF is the one that is wrapping around the surface of the airfoil. So the entire control volume is given by A, B, C, D, E, F, G, H, I. This is my entire control volume. And the width of this control volume, in that is, it is in the Z direction, which is perpendicular to the page. For example, if you're sketching this on a paper, then it is perpendicular to the direction of that paper. Now let us name these two stations as 1 and 2, and these 1 and 2 represent the inflow and outflow along the control volume. So here we can see we have U1 and U2. So this is the uniform velocity entering the control volume, and U2 is the velocity that is leaving the control volume. Now from the figure you can see that this velocity that is coming out of the control volume does not seem to be uniform. Now why is it so and how is it so is what we will look into this video. So proceeding further, let us see what are the assumptions that we have taken in order to calculate the drag. So the assumptions that we have considered over here is that the contour ABHI, that is the control volume which is far away from the body, ABHI, it is far enough such that at every point, everywhere on ABHI, the pressure is equal to free stream pressure. That is, my free stream pressure is given by P infinity when the flow is entering the control volume. So here I would say P is equal to P infinity at these two streamlines, that is over here. This P is equal to P infinity is at these streamlines AB and HI. The reason being that they are very far away from the second assumption is that inflow velocity U1 is uniform across AI. That is, this is the AI, and my uniform velocity inflow velocity is uniform across AI, as it would be in the free stream. For example, if you're putting your airfoil in the wind tunnel, so whatever velocity is entering the inflow, that would be the uniform velocity. This is the second assumption that we are taking. And the third assumption that we are taking over here is that both u1 and u2 are the velocities in x direction. For example, if you're placing this airfoil in a wind tunnel, you will have velocities in x, y, and z directions as well. But we are assuming over here that the velocities are only in the x direction. That is, my velocity is varying only in the x direction. But u1 and u2 both are in x direction. But now here we have a change. u1 is equal to constant. As you can see here in the figure, u2 would be a function of y as it is getting distributed at the exit. Now, why is this velocity not uniform? The reason is that there is a presence of wake. That is, due to the presence of this body, a wake is being created at the outflow section, due to which I observe the distribution in velocity. Proceeding further with our derivation, first we are going to consider the surface forces. Now, what are the contributions of surface forces, if we would say, which we had seen in the momentum equation? So initially, if I want to observe the pressure distribution over this surface, that is ABHI, the pressure distribution is given by the negative integral of PdS, and this would be across the control volume ABHI. This notation, mathematical notation, might feel pretty much similar to you, as we had done the same thing in our derivation of momentum equation. Now, the surface force on DEF. What is this DEF? This DEF is the control volume which is right around the airfoil and nearer to the airfoil. So there is a surface force created on the control volume due to the presence of the body. So these are the two sources from where we are going to get our surface force. One assumption we can see over here is that the surface shear stress on AB and HI has been neglected. That is, this outer control volume. On this, the surface shear force has been neglected. Now, as you can see, the cuts in the figure, that is this CD and FG, are taken adjacent to each other. So, because they are taken adjacent to each other, what happens is that if there is any shear stress or pressure distribution, it is equal and opposite to each other. So, what happens is they cancel each other. Now, in case if we consider the shear force on DEF, that is in equal and opposite reaction to the shear stress. Whatever shear force is acting on DEF, it is the equal and opposite reaction of the shear stress and pressure distribution which is created by the flow over the surface of the body. Now, what is the moving fluid doing? It is exerting pressure and shear stress distributions over the surface of the body, which creates a resultant force known as R per unit span of the body. Now, what is this R and how does it carry an importance? Let us have a look. By Newton's law, we know that this body is exerting equal and opposite pressure and shear stress distributions on the floor. So based on that, what will be the force on the control surface? This is our D, E and F, and this is our body. So in case, if I look at R, my R would be pointing in this direction. This is the pressure acting, and this is the shear stress denoted by tau. Now, the flow that is passing over this body is exerting pressure and shear stress, giving a resultant aerodynamic force R, as we discussed here in the surface forces, right? And because this is giving an resultant force R, what is happening to the force on the control surface? As we said, Newton's third law, that is equal and opposite pressure and shear stress distributions are being given. So that equal and opposite reaction would be found on this control surface, and that becomes my minus R. We have the surface forces, what are being given. So let us say, what is the total surface force on the entire control volume, which will be given by integral ABHI PdS minus R prime. Kindly note here that this is not body forces, this is surface forces only. Coming back to our equation, so this is the total surface force on the entire control volume, that is outer control volume, ABHI. So let us name this as equation 1. Proceeding further in our derivation, we will consider the left hand side of the equation, the momentum equation, and we will equate that to this equation 1. So left hand side is given by this part of the equation, which gives me, so this is our equation 2 once we equate them. Now, if I say that I want to assume this flow to be steady, so which means this component goes 0, what am I left with in that case? My R prime would be given by rho v ds v minus a integral of ABHI p ds. So for the steady flow, I get R, that is the resultant force, as this. Now this equation 3, it is a vector equation. So what we will do is, we will consider this equation for the control volume, and that is for the x component. We will look at the x component of this equation. So we know the inflow and outflow velocities are u1 and u2. Now the x component of this equation 3 would be the aerodynamic drag per unit span, which is given by d prime. So this is the drag per unit span which we get, that is the x component of R prime. So as you can see, v over here becomes u, and this is x, which was PdS. This is our equation 4. Now, this last term in the equation 4, it is the component of pressure force in the x direction, which is exerted on the elemental area ds of the control surface. Now, we need to recall over here that the boundaries A, B, H, I, as we considered at ABHI or along ABHI, we said that P is equal to P infinity, which means for constant pressure, what happens to this integral? ABHI PdS of x, it becomes 0. This integral becomes 0 in case of constant pressure. Now, if I substitute this in equation 4, what will be my drag per unit span? We will only be left with the first term, that is the cyclic integral of rho v ds u. This would be our equation 6. So keeping this equation in mind, let us evaluate this integral from this equation for the figure that we have considered. Now, as you can see, A, B, H, I and D, E, F are the streamlines of the flow. And also we can see that velocity is parallel to the streamlines, and ds, that is the surface area, is perpendicular to the control. Elemental area ds is perpendicular to the control surface. Along these sections, at these sections, what happens to v and ds? They become the perpendicular vectors, because ds is perpendicular and v is parallel. So v is this, and let us say ds is something this. So they become the perpendicular vectors. And when I say v and ds are perpendicular vectors, what happens to the dot product of them? It becomes 0. So which means, as a result, the contribution of this a, b, h, I and d, e, f to the integral is nothing but 0. So we saw that the contribution of A, B, H, I, D, E, F is 0 in terms of the integral. Let us have a look at the cuts C, D and F, G, which are adjacent to each other. So what happens over here? The mass flux out of one is equal to the mass flux which is into the other. So what happens? The contributions of CD and FG cancel each other. What is the result of this again? The only contribution comes from the section AI and BH. So these are the only two sections which are contributing in the integral of our equation. That is our equation 6. And these sections are oriented in the y direction. Now, we said that the control volume has a unit depth in the z direction. And for these equations, if I want to write the elemental area, it becomes ds is equal to dy of 1. We are considering as unit depth. That is the dz. And these sections, what do I mean by these sections over here? That is the perpendicular sections of our control volume, which is AI and BH. So the sections are AI and BH, because as we saw, all the others have 0 contribution in this integral. Now, if they are having the 0 contribution, what are we going to do? Let us have a look. So now when I say that the contributions are 0 and I have ds is equal to dy of 1, this is what happens to the equation. The integral in the equation becomes this, that is from a to I and b to h, 1 and 2, that is inflow and outflow. Now we have a minus sign over here in the first term right ahead of the integral. What does this minus sign indicate? Why do we have this minus sign? Because v and ds are in opposite direction along ai. That is the reason we have that minus sign. And when it comes to the station HB or BH, they are in same direction, that is in the outflow. That is why the second term has the positive sign. Proceeding further in our derivation, what we are going to do is we are going to get the continuity equation which we had derived in our previous videos. Now this continuity equation, the integral form of the continuity equation, we are going to consider this for a steady flow. So when I say steady flow, this term automatically goes to 0. Then in that case, what am I left with? in surface integral of rho v ds is equal to 0, which is nothing but my equation 7. So I can just substitute the rho v ds over here. So upon substituting and solving, we get this equation, and this is our equation 8. So what do we do here is multiply this equation by u1 on both the sides. So if I multiply the above equation by u1, this is what I get: bh rho 2 u1 u2 dy. Let us have this as our equation 9. So which means this term rho 1 u1 square dy is equal to rho 2 u1 u2 dy. So I can substitute this equation 9 back in equation 7. What happens when I substitute this back in equation 7? Let us have a look. So upon substitution and mathematical manipulation, this is what we get: rho v ds u. Now where can I substitute this term rho v ds u? Can I substitute back over here? That is in my drag per unit span. So I get my drag per unit span as integral b to h rho 2 u2 u1 minus u2 dy. This is our equation 11. Now what does this equation 11 express? If you observe this carefully, what does this equation 11 express? This expresses drag in terms of known free stream velocity u1 and the flow field properties, that is rho 2 u2 across the vertical station, which is downstream of the body, that is at the outflow. How can we know these downstream properties? We can either measure it in a wind tunnel, and the drag per unit span can be obtained by evaluating the integral numerically. And this is done by obtaining the measured data from the wind tunnel. Or one more is we have numerical measured data for these two functions rho 2 and u2, that is density at the outlet and the the velocity at the outlet as a function of y. By using that, we can obtain the drag per unit span. Now if I want to examine this equation 11 carefully, the drag per unit span which we have got in terms of free stream velocity and the flow field properties, we see u1 minus u2. So this term u1 minus u2, it is the velocity decrement given at the y location. It is a velocity decrement. Now why is this velocity decrement happening? Because of the drag on the body. So because there is drag force being exerted on the body, what we see that there is a decrease in velocity. And why is this drag exerted on the body? Because of wakes downstream of the body. And this term rho 2 u2, it is the mass flux. So if I multiply this by the velocity decrement, it gives me the decrement in momentum. This whole term, it gives me the decrement in momentum. So this integral what we are seeing in this equation, it is nothing but physically the decrement in momentum flow that exists across that wake which is being formed, the wakes which are being formed behind this body at the outlet of the flow. So the wakes that are being formed in this way, that is what we are seeing in this equation. Observing this equation, can we come on a conclusion that the wake momentum decrement, that is this part of my equation, the wake momentum decrement is equal to drag per unit span or drag on the body. Now what if I say that I want to write this equation for an incompressible flow? So as we know the condition for incompressible flow, my density is constant. So what happens to the density? It comes outside of the integral dh, and then we are left with u1 minus u2 into dy. So this equation 12, it shows the measurement of velocity distribution across the wake of a body. So this velocity distribution across the wake of a body can give me the value of drag which is being exerted on the body. Now we did this whole derivation, kind of derivation, in order to obtain drag. We introduced momentum equation, then we introduced continuity equation. So what is this all mess about? Why are we introducing these things? First we calculated the forces, then we saw various terms, how they are acting on the control volume, then how they are acting on the body. What is this mess all about? Why do we need to do all this? The ultimatum is that we need to do all this so as to get the amount of drag force which is acting on the body. So in our previous videos, as we discussed, drag is one of the most important force which we need to consider while analyzing the aerodynamic flows. So in order to calculate this drag is what we have gone about all these derivation, and using the conservation equations, that is conservation of momentum and conservation of mass, which are also known as the governing equations. So we have three governing equations. Out of those, these two which we have previously derived in our videos, that is the continuity and momentum equations, and also we saw their application, how they can be used to calculate the aerodynamic forces. On this note, let us end our video over here, and in the upcoming videos we will also see more interesting topics of such sort. So thank you for listening and stay tuned.